Okay, math group, let's get going on Math 115's Unit 6 Desmos activity. We are headed toward the end of the semester, and I would like you to think about some specific things you can do to support your success in the course as we move toward the end. These need to be very specific. When we say things like, oh, I'm going to study more, what does that look like? Be specific with those. These are things to support your own success. From an earlier activity, we had some of these same numbers, maybe in the previous unit. We're going to proceed with the ones that are present. The interest rate is a bit low for the actuality of the world right now. But I'm asking you some questions about this output from a car loan calculator. How much was borrowed? That's the loan amount right there. That's the $8,316. How long was this loan? It was 48 months. And that's also the same thing as 4 years. And then the interest rate, hanging out right there in the center, that 3.05%. That is very low for right now. We are headed toward computing the monthly payment amount, this part down here. We are headed toward being able to find that by hand using a formula. So we need these other components to make that happen. Formula for that is pretty intimidating. So little bits at a time. The PMT on the outside, that stands for the payment. That's the monthly payment that we're looking for. The A, right there on the right-hand side before the parentheses, that is the amount of the loan, the amount that we need to borrow. The R and the N are very much like what you're used to. R is the interest rate as a percentage. N is the number of compounding periods per year. And for us, we're going to deal with monthly payments, so N will equal 12. And then the T in the exponent down there, T is time in years. So I'd like it if we could make a very careful attempt at filling in this formula, just filling it in for this particular set of information over here. So I've copied the formula in here. I'm going to grab the other components. The loan amount was $8,316. The interest rate happens in a couple spots. As a decimal, it is 0.0305. And that also has to go in the denominator. It goes inside the parentheses in the denominator as a numerator of another fraction. Our N values are going to be 12 for monthly payments. So 12 right there. And then I'm going to need to multiply in that exponent. Oops, I have a typo already. 12. It needs to be multiplied by 4. And it needs to be up in the exponent. Well, great. I'll use parentheses. I'll make it happen somehow. Up there in that negative exponent, it should read negative 12 for monthly times 4 for the 4 years. And notice that 12 times 4 gives you that 48 months in the loan period. So I just wanted you to fill this in. That's all I was after here. Just trying to fill in all the components. And then we'll get around to the business of trying to do the computation. So on the next screen, here's what I get for the fill-in. It's the same as on the one before. And then if you're going to do this work by hand on the calculator, these are my recommendations. Do not do any rounding until the very last step of the problem, which seems like that's going to be kind of a problem. Okay, it just seems like there's a lot of stuff to not do any rounding until the very end, but we can make it work. My suggestion would be that you work out this exponent first. Negative 12 times 4 is a negative 48. So do that part. And then once you have that, then work on this entire denominator. And that's what's going on here in number 3. Work out just this part and let it sit on your calculator. Don't even write it down. Once you have that, you can do 8316 times the numerator and then divide by your previous answer. So 8316 times the numerator and then divide by the previous answer, that whole line right there. We'd like to get a final result for that. We'd like to round it to the nearest penny and put a dollar sign on the result. My recommendation is that you try this out on a handheld calculator, see if you can do it in step by step like this. But then we can also put it in the Desmos scientific calculator so that it looks just exactly like this component up here that I've just highlighted, I'm going to copy that. I'm going to come to the Desmos Scientific Calculator, and I bet this is it, but let me clear this out. Oh, where's the clear feature? Oh, it says right there in great big letters. Take off this PMT on the front. Take that out of there. 8316. On the front, little fraction up top, a long complicated denominator. Here's $184.25. That's what the monthly payment should be. So I copied and pasted this one, but if you do it by hand, you put the 8316 on the outside and start your parentheses. And then you can use division to make a fraction, 0.0305, and use another division to make that complex fraction. So you have a fraction up top, down below, 1 minus, parentheses 1 plus, there's 0.0305, divide that by 12. Little exponent feature to the negative 12 by 4. And then you can come out and close those parentheses, even though it's already given you the answer. So you can type it in individual components if you're not in a spot where you can copy and paste things. Okay. Once you have this in here one time for finding a payment, you could just come in and replace what's the loan amount, what's the interest rate, how long are we paying on the loan. You can just fill in the components that you need. For our purposes for this particular question, we're getting a loan payment of $184.25 when we round that off. So let me come back to the Desmos activity. $184.25. The online calculator said $184. Let me make it a little bigger. So we're pretty close to what they got. They probably rounded to the nearest whole dollar. I think this one is done. Now we have Maya. We're going to work on Maya's situation. Wants to purchase a building for a new business. We have the property listing amount. Maya is going to make a down payment of 15%. We'd like to know how much Maya needs to borrow. The down payment ends up being 15% of $125,000, which I think is $18,750. And that means the borrowed amount would be the gap between the original price and the down payment. And so I think Maya ends up borrowing $106,250. So there's the amount of the loan. And then we'd like to figure out the monthly payment for Maya's situation. The formula hanging out down here is already filled in, but I'm going to fill in, instead of the letters, I'm going to fill in the actual values. So we need a loan of $106,250. The interest rate is 3.4%, so 0.034. Our N is 12 because we're going to be making monthly payments. There's another 12 right there. And then Maya is going to pay on this for 25 years. So there's all of our information all filled in. To go get the payment amount, if I copy this from Desmos and take it over to the scientific calculator, I can get a new line. I can paste it in there. I could have also changed the numbers in the quantity or the expression above to make it match the new scenario, or I could have just retyped the whole thing. I'm kind of a copy and paste fan. So Maya's payment is coming out to be $526 and it looks like 23 cents. So let's grab that. $526.23. I'm just double checking behind the scenes to see if I got that the same amount twice, and I did. How much will Maya pay total for the property? That'll be the total of her down payment and all of the monthly payments. Her down payment was $17,500. We found that first, I think. And then for monthly payments, there are 12 months in the year. she's going to be paying for 25 years, and the dollar value of each of those was $526.23. So we need to add all of that up. That'll be her total paid. I think when we do that, we'll get $175,369 total paid. And then to find the interest amount, we can take that total paid and subtract off the original price. So total paid, the original price, it seems like it was $125,000. I have to scroll back up. Yep, $125,000. And when we do that subtraction, we find out that Maya ends up paying $50,369 in interest over the entire life of the loan. It's a lot of interest. It's a lot of money. It might not be a lot of interest compared to a loan at a higher rate or something that goes on for a longer time, but it's just a lot of money if you ask me. And then I think this one is done. Total paid, how much is interest, and we found her payment to get us rolling after we did a little bit of work with a down payment in the beginning. Here's another style of problem. We're going to borrow Maya's information, but we're going to figure out what would the payoff amount be if Maya wants to check out of that loan early. So the payoff amount for something like that, if you want to be done with a loan early, has a slightly different formula. It looks like it's the reverse of the last one, like the denominator has now moved to the numerator, like it's flipped over. And that is true. The components are all exactly what you would expect them to be, but there's one twist. The t-value, that's a lot of highlighting, the t-value represents the number of years that are remaining on the loan, the remaining part. So a little twist there. We would like to find the payoff amount for the loan that is described below. And then we'd also like to know, like, how much do we save by paying off the loan early? There must be some benefit to this. So after 15 years of monthly payments at this rate that we just found for Maya, what's the payoff amount? So we're going to take this formula, fill in the components, being very, very careful about that exponent up there, using a t-value that is the remaining number of years. So here's the formula. Let's fill in that payment. It is $526.23. The interest rate is the same as it was before, the 3.4%, so 0.034. The N value is still monthly, so 12. And then the T value, here's where the twist is. We had a 25-year loan, but 15 years of payments have already been taken care of. And so 25 minus 15 gives us 10 years left on the loan. And this is the computation we'd like to be able to do. If you were going to do this one by hand on a handheld calculator, you would do the negative 12 times 10 first for negative 120. And then you would do this numerator. Sorry, just the numerator. And then you can do 526.23 times that numerator component, and then divide by, I'd put parentheses around that denominator. For me, for right now, I'm going to grab this and go over to the Desmos calculator. So that was an old calculation. Here's the new one. I'm just taking a quick look and making sure it grabbed everything, and I think that it did. And so this is telling us that the payoff amount, with 10 years left to go on the loan, is $53,468.82 when we do the rounding. So equals. I'm a little bit worried it's not going to fit, so let me come down. $53,468.82. So if Maya wants to cash out with 10 years remaining, that's the amount of money she would need to go to the bank with to try to cash out. And of course, this would depend on the paperwork behind the scenes if they even allow cashing out early. The amount saved by paying off the loan early. Oops, yeah, oh, it fixed it for me. Amount saved. I'm going to just put this in quotes. What would we have paid if we had continued with the loan for those remaining 10 years minus the payoff amount? So Maya, continuing for the next 10 years, would have had 10 years worth of monthly payments, so 10 times 12, times that 526 and 23 cents. And then let's take off the payoff amount of 53,468 and 82 cents. And when we do that subtraction, I think the gap between those is, oops, too many decimals or dollar signs, $9,678.78 saved for that. Paying off a loan early, if there are no other penalties or fees for doing so, if you're allowed to do so, will often save you money. And so you want to be able to find that information in your paperwork. And if you're able, you want to pay off loans as early as you can. You're saving interest that way. So, creeping up on $10,000 she saves by paying off early. I think that's the end of that one. So we've been working on consumer loans, which can feel really demoralizing with all of the money that goes to the bank. But here's one, a different style of problem that's a little bit more uplifting. This is about you saving for the future. So we have a new formula for this. It looks like it has all of the same components that we've already been talking about. This scenario involves us making fixed monthly payments for a long time, and they sit in an account and they earn interest, and we don't ever touch that pile of money. We just let it sit there. And in the end, what will that pile look like? How much of that, we want the total for the pile of money. We want the total of all of the contributions that we make, plus all of the interest that we're awarded for that. So FV stands for the future value of the account. Payment will be the payment, usually monthly, that a person puts in. R is the interest rate, and is the monthly component of things. And then T is time in years, just like you're kind of used to. So let's say that we have a KVCC grad. They're going to invest $150 each month for the next 40 years into an account that pays 5.1% interest, and this is part of their retirement plan. We'd like to know how much will be in the account at the end and how much will be interest. So here's the formula, and I'm going to fill it in chunk by chunk. The payment portion is $150. The rate, 0.051. It goes in two places. This person is making monthly payments, so N is 12. Notice that exponent is positive this time. And then the timing is 40 years. If you're doing this one with a handheld calculator, do the 12 times 40 first, get 480, and then do the entire numerator. And then take that answer and multiply by the 150. Take that answer and divide by this quantity in parentheses. Otherwise, the calculator won't know what to do. And for us, I'm going to copy that. Head over to the land of my scientific calculator. I'm going to paste it in there. And I like to just take a second look and make sure that nothing has gone missing or no extra stuff is in my formula. I think it looks pretty good. And so it's telling me that this is my dollar amount off in the future. So let me borrow that. Put a dollar sign on here. This looks like $234,968.34. That is all of the payments the person puts in plus all of their interest over time. How much of this is interest? That'll be the gap between the person's contributions. So the person contributed monthly payments for 40 years of $150. Actually, we should go in the opposite order so we don't get a negative answer. We're still going to use that amount, but we'll find the gap between $234,968.34 minus all of those payments. So the output of the account minus everything that the person put in. And when I did this one a little bit earlier, I came up with a gap of $162,968.34. This is the interest amount. And you might have to pay taxes on this. You may have already done it along the way. Taxes are something that we like to complain about, but we have to deal with them. We don't deal with them in this course though. So just on the surface, we get this future value of the account at about $235,000. We compare it to everything that we put in. We get an interest amount. That's a bonus for us in this case of $162,968.34. It's a bonus question on the end. If we were to adjust that to today's dollars, if we use 3% annual inflation, like in regular times, not these times where the inflation rate has been really scary recently, that brings us back to compound interest with this formula. And so we can fill in, there's a couple different ways to do this, but we can take this dollar amount that we just figured out, and that's going to be the value on the front. 3% interest is 0.03. Interest is done annually, so 1 right there. And we'll have a 1 here. And then the T gets a little twist if we're doing it in this format. We have this $234,000 number that's way out in the future. And we would like to bring that amount backward in time to today. And so we would use a -40 for that. So instead of using +40 and making it go even further out into the future, we're going to bring it backward to today. And when I do this calculation, I get $72,031.15. So if we think about $72,000 today, in 40 years, that would have the same look or feel as $234,968 approximately. It's that adjustment for inflation. Today's $72,000 has the same spending power as it will, or as $234,968 will 40 years from now. So I think this might wrap up our finance stuff for us. I think that might be it. Yeah, because then I switch us over to some statistics. And you have extra practice opportunities on the finance stuff. It is kind of sticky. Let me know if you need help. To find someone's grade point average, this is our first statistic that we'll work on. I have given you this person's set of classes, how many credits each class is work, and the grade they are earning. To find a grade point average, we find something called quality points. And we do that by multiplying the number of credits by the grade in each case. So for Math 115, it's a 4-credit class and the person's earning a 3.0. 4 times 3 will give us 12. For Bio 300, it's a 3-credit class. The person's earning a 2.0. 3 times 2 will give us 6. For A&M 120, 4 times 3.5, I think is 14 quality points. For WPE, not quite sure what's happening there, but it's 2 times 0, which is 0. To find a GPA, we need a total of all of the quality points. So there's 1832. And we need a total of all of the credits. So there's 7, 11, 13. To find that GPA, we need to do 32 divided by 13. And in the instructions, it said to round to the nearest hundredth. I haven't done this one yet. 32 divided by 13. 2.46, it looks like, rounded to the nearest hundredth. And I think that one would be done. If you have a larger collection of classes, like over many, many, many semesters, you would do it exactly the same way, except you just have a longer list of things to do. Some plots are coming our way. Here's a stem and leaf plot in this case. And this is supposed to be 52 students doing something. That's how the key works there. Requesting help at student services on some day. Least number of students. Well, this thing is read, here's 52 students, and then some other day had 54 students, and then 58 and 59, and then we jump into the 70s, the 80s, and the 90s. So the least number of students comes from this top end, 52 right there. And if I ask you about the greatest number, that comes from this bottom row. So these are in the 90s, 94 and then 98. 98 would be the greatest number of students. So least is 52, the greatest is 98. I skipped over the mean because it takes a little bit. For the median, well, the median is the middle of things. Let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. It looks like there were 14 days where they had these records being kept. And so if you take half of 14, you get 7. So 7 entries on the lower half and then 7 entries on the upper half. Let me clear out some of this. All right, let me get a new color. If I count to the 7th entry, 1, 2, 3, 4, 5, 6, 7. Here's the 7th entry from the low end. 1, 2, 3, 4, 5, 6, 7. Here's the 7th entry from the high end. So if we're going to talk about the middle of our data set, we're going to be in an argument over whether to use 72 or 75 or something in between. And we want to use something halfway in between those two. When you don't have an exact middle entry, take the average of the 2 in the center. So we'll take 72 plus 75 and divide by 2. And I think when we do that for the median, it's essentially the mean of the 7th and 8th entries. We should get 73.5 students for that. The mode of the data set is the most frequently occurring entry. And when I look through here, I don't have anything that repeats. It looks like maybe an 8 repeats, but remember this is 58 and this is 88. Those aren't repeats. So we don't have a mode for this data set. Nothing is repeating in those rows. And now we get to go deal with the mean. For the mean, we have to add up the total of all of the entries and then divide by 14. So to find that total, you can type them all in your calculator one at a time if you would like to. It's maybe not the most fun you've ever had, but it's possible. When I do these, I find the total of the top row. So I add 52 plus 54 plus 58 plus 59 and find that total. And I write it down. And then I come through and I do the 70s. So 70 plus 71 plus 72 plus 75 plus 77. And then I come through and I do the 80s. And then I come through and I do the 90s. And then I add all of those together. So I actually don't type them all in one giant list. I used 4 smaller lists. When I did that, you can double check your own work, which I'm hoping you are doing. When I did that, I got a total of, come down here and put in 1,033. And I need to divide that by 14. And so my answer here ended up being 73.7857-ish. Let me round it to the nearest tenth. 73 point, oops, lost my equals. 73.8 students was the average amount. And an average is supposed to be a measure of center. And so it does need to be between the low end of 52 and the high end of 98 students, and it is between those two. So if I have an error, it's not way off. I'm in between the low end and the high end. It's a reasonable amount. We'll see what you get. You would let me know if you get something different. Otherwise, I think this one is done, other than you fact checking me. Least, greatest, mean, median, mode. Yep, think so. All right, this is called a frequency table. Here's another way of organizing information. This one says, okay, we have 3 students who visited the Math Center 0 times this semester, and then we have 8 students who visited once each, 5 students who visited twice each, and 4 students who visited 3 times each. So we'd like to know a few different things. How many students were reported, or how many students were surveyed altogether? That's going to come from the top row in this case. 3 plus 8 is 11, plus 5 is 16, plus 4 is 20. So I have a vote for 20 students total. How many reported visiting the Math Center at least once? That means 1 time or more. So that would come by looking at the bottom row. We need those who went once or twice or 3 times, which will just be this 8 and that 5 and that 4. So 8 plus 5 is 13, plus another 4 is 17 students. For less than 3 times, that means they don't get to go 3 times. They can only go twice or once or none. So that would be these 5 went twice, these 8 went once, and these 3 didn't go at all. So there's 13 plus another 3 is 16 students that went less than 3 times. That's how I get that. And then letter D is a little bit stickier. Average number of visits per student. To do this one, we want to find the total visits that were made and divide by the total number of students that were surveyed. We already know the total students surveyed was 20. We had that in letter A, but the total visits made is a little bit stickier. So maybe I just give myself some more space here. For total visits, well, we have 3 students who went no times. So 3 times 0 is 0 visits. And then 8 students who went 1 time. 8 times 1 is 8. 5 students who went twice. 5 times 2 is 10. 4 students who went 3 times. 4 times 3 is 12. So we need to add up 0 plus 8 plus 10 plus 12. And once we have that, we'll divide by 20 students. So it looks like 18 plus 12 is 30. Divide that by 20. This is 1.5 visits per student on average. So I think the sticky part here is this sum, because we have to get that sum by looking at the table and saying, oh yeah, 3 students went not at all. That's 0. 8 students went 1 time each. 8 times 1 is 8. We have to find all of those products and add them together. All right, mean, median, mode, and range for this data set. For the median, we'll want things to be in order, so I put them in order from least to greatest over here in the sketch box, and I hope that I caught everything correctly. Just going to do a quick double check. 1, 2, 3, 4, 5, 6, 7. Yep, 7 entries, and as long as I copied them correctly, we'll be in business. To find the mean for letter A, we'll want to add up all of those entries and then divide by 7. The median needs to be the middle entry, and when you have 7 entries, an odd number of entries, we will have an exact middle, and it's right there. As there are 3 entries below it and 3 entries above it, this is the exact middle. So letter B ends up being 48 minutes, and it's friendlier than last time. The mode of the entries is the most frequent of the entries, and there can be no mode or one mode or more than one mode. This one, I think 48, is going to also be our mode as well as our median. And then the range, that's the gap between the high end of our data points and the low end. So we'll be comparing 72 and 12. So let's see what those came out to be. The mean should be the total divided by 7. And looking for my total, I get a total of 320 when I did this. So 320 divided by 7, let's call this 2 decimal places, 45.71 minutes. So you do 320 divided by 7, make sure that you get the same thing as me. The median was going to be the middle entry. It's got those arrows on it. It is 48 minutes. The mode was also 48. And then the range, the high minus the low, 72 minus 12 is 60 minutes. We also get box and whisker plots. We get a little intro to them, and they can look like they're very fancy and maybe a little bit intimidating, but all the box and whisker plot does is take all of our data points and chops them into groups of 4, or not groups of 4, chops them into 4 groups. So we have, like the median splits the data set into 2 halves. The box and whisker plot will separate the data into 4 quarters. So let's pretend that these are percentages earned on some test in Math 5000. You can make this bigger with the expander. I'm going to ask you some questions about this. The minimum score, I think it's supposed to be 68, but that one's a little bit hard to tell. But the minimum coming in around 67, 68. Q1, or the first quartile, this one is coming in at 70%. Q2, which is also the median, is coming in at 74%. Q3, the third quartile, also called the 75th percentile, or the upper quartile, lots of vocab there, that's coming in at 85%. And then the maximum looks like it's coming in at 92%. So let's see if we can use those numbers to answer some questions. Minimum percentage, maximum percentage, and the median, A, B, and C. I think we just mentioned those. This one, for the minimum, it was kind of hard to tell exactly. So when I run this in class, I usually get a couple different answers running around. The maximum and the median we usually agree on, 92% and 74%. And then there's this twisty question at the end. 400 students took the test. How many scored between 70% and 85%? So in my picture, 70% is right there and 85% is right there. And that means that we need to use these boxes on the box and whisker plot. We use 2 of them, and they account for 1/4 of the data points each. So 2 sets of a 1/4 is a half. Or you can think of it in terms of percentages. 25% live in this little smaller box, 25% live in the second box. And so we have 50% that we're worried about. 50% of 400 people taking the test is 200 students. So a box and whisker plot gives us an idea of how tightly packed the data points are. Things are really tightly packed in this left-hand portion of the box because it's small, it's narrow. But then this one over here on the right, this one is very long comparatively. And so the data points aren't as tightly packed in there. They're further apart, they're more dispersed. And then I ask you, how did things go? We're going to do some more work with box and whisker plots in the next unit, but there was a little bit of an intro here. As always, if you need something, please reach out. I'd be glad to try to help you out with things. And if you spot any errors, let me know those too, because your classmates will want to know.